Okay, so welcome back. Before we begin, a couple of usual administrative things like A3 has been graded. Like we should have released it before the lecture, but we are going to do it right after the lecture. And about the Kaggle competition. So I think currently there are like approximately 10 teams who have started participating. Like, but there are probably 20 to 25 more teams like who haven't even started. Okay, so you cannot get good scores in the last 4 attempts. Like, so you should really utilize the 2 attempts that you have every day. So my general tip is first try to set up your pipeline for the task as soon as possible. It's okay even if your algorithm is like really dumb. Like, so you should try to make some prediction, like come up with some predictions and submit it by today or tomorrow. Okay, so aim to have a couple of submissions by tomorrow. Like, so it's okay if it is a simple logistic regression. Okay, so like what matters is like you have the whole pipeline set up. So then you can improve your algorithm like every day. So you have only 2 submissions per day. So for every week that you're not making any submissions, like waiting for finishing your setup, like so you're losing a lot of submissions. So I really hope to see all the teams in by this week, like so that you know like where you stand and like you can continue improving your scores. Like, so are there any general questions or feedback about the Kaggle competition? How is it going? Okay, how many of you in the class have started working on your Kaggle competition? Okay, a lot of you in the class, like people in the Zoom can hand raise. I can count the hand raises. Okay, everyone is raising hand. Okay, so well, it looks like all of you have started, but you haven't made any. Some of you haven't made any submissions. So try to make submissions as soon as possible. Okay, so that is about Kaggle, and so we have 3 more lectures, including today's, right? So and for the finals, whatever the exam date that has been given, like we will do. I'm not sure. Okay, I confuse which class I give these information. Like, so have I talked about finals in this class, or it was reinforcement learning course? I haven't talked about finals here. Okay, so when is the finals?
18.
Sorry?
18 of December.
Is it 18 or 17?
18.
18th afternoon, is it? Okay, so the finals is okay. So there is okay. So there is a question about final. Okay. So okay, I will come to the question. So it's on 18th at 1:30 p.m. Okay, so I think the question is very important. Somebody is asking why is a room number given for the finals? Okay, so that's a mistake from the university side. I have asked them to remove that from the schedule. Okay, so don't go to that room number for your finals. Like, so your finals is going to be online, so you can do it from home. If you are traveling around the time, like you can go to your home country and like do it from there. Like, it doesn't matter, but the time will not change. Like, so like even if it is midnight for you in a different country, like so the time for the finals is 1:30. Okay, it's from 1:30. I will ask the university to remove the room number and mention that it is online. Okay, and the exam is going to be set for 2 hours. Okay, so it's 1:30 to 3:30 with an extra hour like for you to upload your answers in grade school. In case you're handwriting your answers, like so then you can use the time to scan it. If you're typing your answers in document or LaTeX, like then probably you don't need the time. But there's one thing that I want to highlight. So you have that complete 3 hours to write your exam. Okay, so the exam is set for 2 hours. Like, this happened last year's finals. Like, so there were some really sincere students in the class. Like, by the end of the 2nd hour, they did not finish the exam, but they thought they should stop. So they submitted by next 5 minutes. However, there were a lot of students in the class who utilized the extra hour to write and submitted by end of the 3rd hour. Okay, now to make it fair for everyone, if you want to write your exam until 4:30, you can do that. Okay, exam is from 1:30 to 3:30, then you have extra 1 hour buffer. You can use it for writing the exam if you want. But given the fact that I'm giving you 1 hour buffer, even if you submit it by 4:31, you get a 0. Okay, so I will not accept any excuses. So you cannot say, oh, it was last minute, like my internet was not working, or like I took extra 5 minutes. No, you're not taking extra 5 minutes. You're taking extra 65 minutes. Okay, so no more submissions after 4:30. So we'll in fact close the submission. You cannot submit it after 4:30. So 1 hour is a lot of time for you to scan and submit. So you should aim to submit by, let's say, 4 o'clock, not 4:30. So if you go up to 4:30, you are taking the risk. Okay, so like, please don't email me your answers. Yeah.
Will the exam be made so that it is realistic for us to finish it in 2 hours?
Yes, yes. Okay, so I will not set up a 3-hour exam and ask you to do it in 2 hours, which means you're going to have more time to do the exam.
Just have another question. Is the exam going to be monitored on like a proper exam, and if so, how many cameras will you need?
Okay. I don't like these online monitored exams. Okay, so you're all adults, and that is another reason why we are doing open book exam. So the exam is open book. Okay, so I highly discourage you to like directly Google the questions and try to come up with the answer. At the same time, of course, there are certain things that you should not do, which is considered as cheating. You cannot call your phone, like call your friend, or you cannot write the exam together. Okay, but I'm going to trust you guys. Okay, so if I want to set up a monitored exam, I can do that. University is giving all the resources. Okay, they are going to put invigilators who are going to watch you through Zoom, all the 100 of you, but I think it is not necessary. Okay, so like you will be signing a honor code, and I expect that you all respect that honor code. So the exam will not be monitored through Zoom or like through web camera. Like, so you're writing it by yourself, and you sign and promise that like you did not cheat. Okay, so yeah.
Can we resubmit in the time? I mean,
Oh yeah, you can resubmit it. Oh, that's a good strategy. Like, so if you want to be sure that you don't miss the deadline, you can submit and then resubmit if you want. In GradeScope, you can resubmit.
We're gonna have the lectures exam.
Yes. Okay. I will release last year's exam probably. Can you remind me after the class? Okay. So I will release it today, because the point is it was an online exam, and some of you already might have access to the exam paper from friends. So it doesn't make sense to not release it. So I will release the previous year's question. Any other questions?
and also, should we just submit it in the GradeScope and by labeling the questions?
Yes. You will be submitting it in GradeScope by labeling the question. So there is some labeling time involved.
What would be the best way to prepare for the exam in your opinion?
Okay. Well, as I keep repeating, like, so if you are very comfortable with all the self-assessment questions, then probably you have the right background. And I think just going through the lecture notes, and like I'll release the final exam from last year. It will give you an idea of like what kind of questions you can expect. But just the lecture notes, like I will not ask anything which is outside the lecture. Like, of course, like you'll be applying concepts from the lecture notes, which means it's going to be more than like what is there in the notes. Like, but the requirement is you have mastered the lecture notes.
Are we gonna have to like write down equations or like circle?
Possibly. Well, if you have to write something anyway, you have access to the notes. Like, so then you can imagine like what kind of question. I'm not going to ask you to, like, for example, derive Newton-Raphson, because it's already there in the lecture notes, right? So any other questions? Okay, so there are a couple of questions in the chat. So extra 30 minutes. Yes, I think I have already answered it. There's a question about how much math notation involved. So I don't know what you mean by math notation, like whatever math that is there in the lecture notes. And Is it the same format for oral course? Yes, I think I talked about it last week in the class. I think I answered all the other questions directly or indirectly. Any other questions about exam? Yeah.
Is it Gradescope or Moodle?
Gradescope.
Okay.
Okay. So, and I think I already mentioned this last week. Like, so, don't stress too much about assignments and exams. Like, so I will be leaning to the end. Like do your best. Be honest. Don't cheat. Okay. So that's not the point of the course. Okay, so let's get started. So given that we kind of rushed through convolutional networks last week, like, so I wanted to give a very quick summary of like concepts, like before we move to topic of today's lecture, which is advanced optimization. Okay, so if you remember our discussion from last week, right? Like, so almost all the algorithms that we have seen so far in this course, like, expect the input to be in a form of vector, right? Like, so, like, you consider logistic regression or neural networks or like what else, like simple linear regression, SVMs, like, so whatever you take, like, it expects a vector as input, right? Like, so now sometimes input has a lot of structure and probably you want to exploit this structure, like, so when you are designing your machine learning algorithms, right? Like, so one good example that we saw last week is about images. So in the case of images, you often have this probably a 32 cross 32 pixel image or 1K cross 1K pixel image, right? Like, which is a matrix. Now, this is not just a matrix, like, it has RGB channels, right? Like, so red, green, and blue channels. Like, so it is really a n cross 3 tensor, right? Now, if I have to use a vanilla multi-layer perceptron to do this, like, so which is what you see in the left-hand side, right? So first I need to flatten out this image. If it is 32 cross 32 cross 3, like, I flatten out into a single vector and I pass that single vector here, and then I have a bunch of layers and then classification, right? Like, so now we did some calculations last week that, like, if the quality of this image increases, like, as you have more and more pixels, then you're going to have millions and billions of parameters in your first layer, like, because there are too many pixels and every unit has to connect to all the pixels, right? Like, so this could lead to overfitting, right? Like, and also it has other issues, like, for example, you need lots and lots of data to train such an MLP, right? Like, so now, is there a better way to handle images? Like, so that's where we discussed about convnets. Like, so where the idea is you have a layer which we are going to call as convolutional layer, which takes a 3D volume as input and also produces a 3D volume as output, right? So you can see here, like, you pass the image, which is 32 cross 32 cross 3, okay? Then you have a convolutional layer, okay, which converts it into another tensor representation, then another tensor representation. So finally, if you have a 10 cross 10 if you have a 10 class problem, then you get a 1 cross 1 cross 10. You can flatten it out. Okay. Now, we discussed about how this is actually done inside the convolutional network. Like, so the basic idea is you're going to have a bunch of small like filters, right? Like, so, like, for example, you could have a 3 cross 3 filter, which means, maybe let me, yeah. In this case, like, I have a small 5 cross 5 filter. Okay? Each filter is going to look for some characteristics or like some feature. Like, so for example, I think we talked about this eye filter, which is looking for an eye, right? Now this filter is going to be applied in the image, like patch by patch. Now, how do I move from the first patch to the second patch? That is controlled by the stride parameter, right? Like, so if my stride is 1, I move 1 pixel at a time. If my stride is 2, I move 2 pixels at a time. So the advantage of having bigger strides is, like, now I'm going to have smaller output. So the number of parameters required is going to reduce, right? Now, we also talked about, like, how to zero pad this image. Sometimes if strides doesn't fit exactly, we just put a 0 in the corners, like so that like sides match, right? Like, or sometimes when we want to keep the same size, we could add zero padding, right? So now once you put all these things together, like, so what's tried to put, what is the size of the filter, how many filters you want, right? Like, so you do all these calculations. So then a convolutional layer will basically implement a convolution function which convolves over the image, like by striding, and produces an output. Is that clear? So any question? Any question? Okay, so I think we also talked about pooling layers, which is basically like taking a bunch of values and like just do either max pooling or average pooling, right? So, and finally, a typical connet would look something like this. Like, so you first do a convolution layer. Like, so now convolution is a linear operation. Okay, so if you cannot just do two cons without a nonlinearity. So then you add a nonlinearity, like in this case, we're adding a ReLU, then another con, then another ReLU, then probably a pooling layer. Like, so, and also as I mentioned towards the end of the lecture, it is now like old fashioned to use pooling layers. Like, nobody uses pooling layers. Like, so if you want to pool, like, you can just increase the stride in that layer. So just increase the stride from 2 to 3, you're going to get smaller output. Okay, so is that clear? Okay, so now I think we can move to today's topic. So, okay, so now we are going to revisit some of the fundamental concepts in machine learning. Okay, so now in the beginning of the course, like, so probably in the second week, we looked at gradient descent as a way to learn, right? And I think for the entire course, like, so we have been using gradient descent as one of our common tools whenever we have a function that we want to minimize or maximize, right? Now, so this gradient descent is an example for an optimization method. Okay. And today we are going to talk more about optimization and like what are the improvements that we can do on the top of gradient descent so that we can minimize our functions faster and like learn faster, right? Like, so now we are going to look at gradient descent variance. Okay, now let us assume that we have a data set which is a bunch of xi's and yi's. Okay, and there are t examples in the data set. Okay, now, so we have seen like a few varieties of gradient descent so far, right? Like, so the first the first variant or the original gradient descent is this idea of full batch gradient descent. Okay, where you essentially go through the entire data set, compute the gradient, sum it, and then make an update. So let's say theta is your parameter. Like, so now theta is going to be theta minus some learning rate. Okay, like I think sometimes we call it as eta, sometimes we call it as alpha, like some learning rate, multiplied by the gradient with respect to some cost function. Okay, now this is based on the entire data set. Is that clear? Now this is like the full batch gradient descent. Like, but if you have 100 examples, you compute the gradient with respect to all the 100 examples, and then you make an update. Okay. Now, as you can imagine, this is going to be very slow because if let's say you have 1,000,000 examples. Now, to take one step, you have to go through all the 1,000,000 examples, right? Now, it's going to be slow. And also, like, it is not possible to use this to update a model completely online. Okay, so imagine examples are coming in a stream. Okay, like let's say you have a deployed machine learning system it gets example. Because of privacy reasons, you cannot store examples. You have to learn from the example and throw it away, let's say within a day or two. Okay. Now you cannot wait to collect all the examples and then make an update. So you have to make your update as soon as possible, right? Like so. Now in those situations, like you cannot use the batch gradient descent. Okay. Now, however, it has some nice properties in the sense if you have a convex function that you want to minimize, we know that batch gradient descent will converge and it will converge to the minimum, right? Like so. And in the case of non-convex functions, it is going to converge, but converge to a local minimum instead of a global minimum, right? So now that is full batch gradient descent. Now we also discussed a variant of gradient descent, like which is stochastic gradient descent. Right? So if you remember what is SGD, like so it is like a stochastic version of this batch gradient descent. So it is going to sample one example and make an update with respect to just that one example. In that sense, it's going to be faster than full batch gradient descent because it doesn't wait for all the million examples. It takes an example and updates. It has already learned something before seeing the second example. Okay. Now you can use such algorithms for online settings, like so where like data comes in, you compute the gradient, you update your model, throw the data, right? So now it is very useful to do stochastic gradient descent in online settings. Now the update equation for stochastic gradient descent is going to look something like this. It's going to be theta is equal to theta minus eta, the gradient of the cost function. Okay. Now instead of using the entire example to compute the gradient, I'm just going to use one random ith example to compute the gradient. Is that clear? Now, one thing we should remember is this stochastic gradient, right? This is just an approximation for the true gradient. Okay, so the gradient that you see here, that is the true gradient if you want to minimize the loss function, because that is the gradient with respect to the total loss function. Now, this second gradient that you're seeing here is an approximation. In the sense, this is a gradient with respect to loss for one example, not all the examples. Now, there is no guarantee that taking this step is going to help you to minimize the total loss, right? On an average, you will go towards the right direction. But if you just look at one update, probably like it might not be the right direction. Like you're going to have a lot of variance when you do stochastic gradient descent. Okay. Now, here is an example learning curve, like when you use stochastic gradient descent. Okay. Now, in the same place, have you used a full batch gradient descent? Your loss will always decrease monotonically. Okay. However, when you use stochastic gradient descent, your loss is going to fluctuate a little bit. Simply because you have a stochastic approximation and there is a noise in stochastic approximation which could lead to like high variance. Is that clear? Now, so this fluctuations are actually the main reason why SGD can skip local minimums, right? Like so now in the case of full batch gradient descent, let's say I have a loss function like this, okay, and let's say I start here. If I use full batch gradient descent, there is no way I can skip this local minimum. If I start here, it will always reach here, right? On the other hand, if I use stochastic gradient descent, let's change the color. So let's say I use stochastic gradient descent. So then maybe from here I go here, then maybe accidentally I could go here because of the variance, if I'm lucky. So then I go here, and reach here. Is that clear? So this is possible because of the fluctuations that you see in stochastic gradient descent, while it is totally not possible with full batch gradient descent. Okay. However, the issue with SGD again is like because of the variance, sometimes you could overshoot. So it is also important that you slowly decrease your learning rate so that you can have the same convergence behavior full batch gradient descent. Okay. Now, in one extreme, we have this complete data full batch gradient descent, which requires you to go through all the examples, right? So you have full batch gradient descent, and in the other extreme, you have stochastic gradient descent, which requires only one example. So this requires T examples, while this requires only one example. Right? Now, can we do something which is better than this, right? Like, so can we have something which has less variance than SGD? Okay, it is possible. Like, so one can do a mini batch gradient descent. Okay, we're going to put it here. Okay. So the idea of mini batch gradient descent is just to take the best of both worlds. Okay, so the advantage of SGD is it is faster, like you do updates quicker. The advantage of full batch is it has no noise, right? Like, so can we get something which is less noisier than SGD, but more faster than full batch, right? Like, so that is mini batch gradient descent. So what we normally do in mini batch gradient descent is, like, instead of taking one example, I'm going to pick some K examples. Now I'm going to compute gradient with respect to these K examples. Okay, let's just say I'm going to pick N examples because that's what I have in the notes. Like, so, like this requires N examples. Okay, where N is much lesser than P. Like, for example, you could have 1,000,000 examples in your training set. You have a batch size of 100. So you randomly pick 100 examples, you do the gradient update. Then you pick the next 100 examples, you do the gradient update, and so on. Okay, so the loss function will look something like this. So theta, the update rule. So theta is equal to theta minus eta times the gradient. Okay, but it is computed only based on xi to I plus n and yi to I plus n. Is that clear? Now this reduces the variance, which means you can converge more stably. Okay, so but there is also another additional advantage for using mini batch gradient descent, which is the fact that when you use stochastic gradient descent, you have only one example. Okay, if you use a complex algorithm like neural network, okay, now we know that neural network has a bunch of matrix operations, right? If you feed in one vector, which is one example, then you have to do vector matrix operations. On the other hand, when you feed 10 examples or n examples, you're feeding a matrix, right? So you're doing matrix operation, which is actually much more like, which is a better utilization of your CPU or GPU, okay? So especially GPUs. Like, so when you are using GPUs and you are doing like one example at a time, you're kind of underutilizing your GPU. On the other hand, like if you do n examples, sometimes people try to increase their mini batch size as much as possible so that it fits your GPU. Like, so for example, well, also typically when you see people using mini batches, they don't use 100 or 200, like they use 64, 128, like 512, 1060, 1024. Because if you have your mini batch, if you have your mini batches in powers of 2, then those matrix operations are much more efficient and hence faster. Okay, so normally when you read machine learning papers, like you'll see people saying, okay, I used a batch size of 512. Okay, so it's a good idea to increase your batch size in powers of 12 and see whatever batch size fits your GPU. And as you can imagine, like this batch size is also a hyperparameter. Like your learning dynamics is going to be different for different batch sizes. So you can tune your batch size by trying few batch sizes, like whenever you are working on a new problem. Is that clear? So any questions about these three basic variants of SGD? So we have seen full batch in one end, stochastic gradient descent on another end, like a mini batch in between. Okay, now this is vanilla gradient descent still, right? Like, so now what are the challenges like that we would face, like if we are using this vanilla gradient descent in different problems? Okay, so one of the major difficulties of using gradient descent is really choosing a proper learning rate. Okay, As I mentioned before, the learning rate is one of the most crucial and most sensitive hyperparameter that you will see in any machine learning algorithm. Okay, so you change your learning rate just a little bit, you will see that your algorithm is not learning, or it is shooting, overshooting, like, or it is diverging, or it is crashing because of numerical precision and so on. Okay, so learning rate plays a crucial role. Like choosing a proper learning rate is very, very important. Okay, so for example, if you choose a very small learning rate, it's going to be more stable, right? Like you will not overshoot. You're taking tiny steps at a time. But then the problem is you have a really slow convergence. Okay, so when you have too small learning rate, you have slow convergence. Okay, now at the same time, let's say you want to learn faster, so you have too large learning rate, then this could actually hinder your convergence, and it could even diverge. So you need something in between. Like, so you need a learning rate which is not too high, which is not too low, and finding this learning rate is a tricky business. Okay, so this is one of the challenges. Now, this is not the only challenge. Okay, so there are few other challenges that you would face, especially when you're working with like modern machine learning algorithms, like and gradient descent. Now, the second issue that you could face is these learning rate schedules, they need to be adjusted. Like, so you have to slowly anneal the learning rate and reduce it over time. Okay, now how to anneal the learning rate? So what schedule to use? So that is one of the practical issues that you would face. Like, so should I reduce my learning rate for every epoch, or should I reduce my learning rate for every 10 epochs? Should I decrease it in an exponential fashion, or like should I decrease it in some other fashion, right? Like, so these are the questions which are very hard to answer. There is no right answer for this. You have to spend a lot of time in finding a right schedule that works for you. Okay, but there is also another issue, which is we are really using the same learning rate for all the parameters, right? Like, there is only one eta, right? So one eta for all parameters. Now, this is going to be a problem if your data is sparse. Okay, let us say my data has 10,000 features. So have we seen such a data recently? Where? In your assignment, right? Like, so you had this 10,000 dimensional vector. Now, on an average, how many words were there in a document? Definitely not 10,000, right? So probably 20, 30 words in a document, right? Like, so in a review, right? So now, which means you have this 10,000 dimensional vector, which has one only in 20 places. The rest is all zero. And also out of these 10,000 words, there are only 100 or 200 frequent words. Most of the words are infrequent, which means you're going to see them very rarely, right? Now, the gradient for those weights connecting with these sparse features, right? Like, so they have the same learning rate alpha or eta as the gradient for the input vectors, like which are more frequent, right? So which means when you start with random initialization, let's say this is my vector, and let us say this is the most frequent words, just for hypothetical example. Okay, now, so these are the most frequent words, which means if I'm using a neural network, let's say I have a bunch of connections coming out, right? Now, connections corresponding to these pink regions, so they are going to get updated more often than connections coming from here. So if I have randomly initialized weights, then these weights are going to stay very close to random. However, these weights might be fine-tuned for like many updates, right? So this is a serious problem. Like, so why is it a problem? Because now there are some parts of your model which hasn't been trained properly, simply because you're using the same learning rate, and there is an advantage. There is a disadvantage like, for sparse features. Is that clear? Now, how do we solve this issue? So I'm going to let you think about this particular issue, like how to solve the situation where like some examples are more frequent, like some parameters get more frequent updates while others doesn't. But we are going to go back to some of the, we are going to talk about the first two problems now, like and talk about this third problem in the end. Yeah.
Can we do rate the do a better pre-processing to put a higher value on more important features, let's say, to the pre-processing?
Well, pre-processing is not going to solve this issue, right? Like, so unless you learn a very dense representation, like which if you're again doing the gradient descent, you have the same problem, right? So the pre-processing is not going to solve this issue. So we will see how to solve this issue like before we finish our lecture today. But for now, I just wanted to list these issues. Okay, so now we will talk about some of the variance or advances over gradient descent, okay, which is going to solve like some of these issues that we discussed. Okay, so we are going to, let's just call all these algorithms as gradient descent plus plus. Now, the first idea that we are going to talk about, like in improving gradient descent, is the idea of momentum. Okay, now when I talked about, or when I introduced gradient descent, probably in week 2, right? So the intuitive explanation, like or like illustration or analogy I gave for gradient descent was someone like blindfolded walking down the hill, right? Like, so let's say you're here and like you have to find the minimum, right? Like, so if you're blindfolded, you will find the descent by using your leg, and like you will slowly go towards it, right? And eventually you will reach here. Now, imagine that like instead of you going down the hill, like so you are in the top of the hill and you put a ball, and this ball goes to the minimum. Okay, so how would the dynamics of that process be? Yeah. Okay, well, yeah, so we have some issues in the end, like so where it might go up, like, but what about before that? It's going to accelerate, right? Like, so like it will start rolling at some point, like if it is going in the same direction, like it will slowly gain some momentum, okay, and accelerate and just move faster. But of course you have this issue, like if it is moving faster, then it might go like this, or sometimes it could even, let's say I have something like this, okay. So sometimes like worst case, it could even jump and go and land here, right, which we don't want it to happen. We are going to fix that issue, but for the moment, let us forget that issue. Okay, let us just think about this idea of like accelerating the speed and how do we implement that in our gradient descent algorithm. Okay, now this comes from the observation that like whenever you have like some sort of like steep regions, gradient descent struggles. Okay, so here is an example. So this is a contour map of my last section. Okay, now imagine the same thing in 3D. Probably I should have had the 3D version here. So like it is a cone, but like a like you pressed it in one direction. Okay, so it's going to be something like this. Okay, now this is my minimum. Let me change the color. So this is my minimum. right? This is where I have to go. But as you can see, along the x-axis, like the surface is a little bit steep, right? So what happens is like when your algorithm starts here, it is going to like just jump between the two sides, and it's going to have a lot of fluctuations before it reaches here. Okay, so this kind of oscillations are very common in SGD. Now, instead of using plain SGD, had I used the concept of momentum, then we know that the gradient that I'm getting for this direction is fluctuating, but the gradient that I'm getting for this direction is always consistent, right? Like it is a small gradient, but it is always pointing me to this place, right? Like so if I made this observation that I'm getting consistent but small gradients towards this direction, then I can accelerate and go towards that direction. Is that clear? Now, how do I do that in equations, right? Like so this is how we are going to do that in equations. So we are going to start maintaining our past gradients. Okay, let us call that like the vector which maintains the past gradients as some vt. Okay, so vt is going to be gamma times vt minus 1 plus eta times the current gradient. Okay, and whenever I want to make an update to my parameters, theta is going to be theta minus vt. Is that clear? So this is SGD with momentum. Now to compare this with vanilla SGD, so vanilla SGD is going to be theta is equal to theta minus eta times the gradient. Is that clear? Now, so this gamma that you see here, right? So this is called momentum coefficient or friction coefficient. Like, so how much friction do you have for moving towards this direction? And usually you will set it to something like 0.9. However, this is a hyperparameter which you should tune, okay? But the usual range is like 0.8, 0.9, or 0.99, and so on. Is that clear? Now, the advantage of doing something like SGD with momentum is like, now you can see that you are actually going faster towards where you want to go. The fluctuations would reduce, like, or in some sense, you are dampening these oscillations by gaining momentum. Is that clear? So, any question about this setup? Yeah.
Is this method applied on all types of gradient descent as in batch, mini batch, and?
Yeah, you can use it in all three variants of mini batch, like for all three variants of gradient descent.
And expect the same behavior?
Yes. Well, in general, it should always give you acceleration, so you should get better performance. Yeah.
Are state-of-the-art models using this?
Okay, so state-of-the-art optimization methods have some momentum, okay, but it is not just momentum. So we are going to talk about several improvements over this today. So, but the state-of-the-art optimization methods definitely use momentum. So this is like a kind of neat trick, which is very obvious, right? Like, so if you are going towards a direction, you should have some momentum. It is always going to help you. Yeah.
Is this method going to help us increase the accuracy, or is it just going to help us?
Okay. Here's the thing. All these improvements over gradient descent that we are seeing today, right? So today's lecture is more about optimization, like, so which is different from machine learning in the sense, in machine learning, we care about generalization error, right? But in optimization, we care about reaching the minimum, okay? So what all these methods are providing you is a faster way to reach your minimum. Now they are all going to the same minimum at in some sense, right? Like, so maybe if there are many minimums, there are probably some of them will go to different minimums. That's a different story. But at least in convex setting, SGD and also SGD with momentum is going to go to the same minimum. So let's say this is my function. Like now, SGD might take 100 steps to reach here, but probably SGD, let's say 100, just an example, okay? So SGD might take 100 steps to reach, but SGDM will, let's say, only take 20 steps to reach. So this is only accelerating the optimization process, okay? So this has no guarantee about generalization whatsoever. However, you might see different generalization behaviors, and this is a topic of research. Like, so there's a lot of work going on like how these kind of modern optimization methods help in generalization. Okay, so but we will not get to that in this course. There was another question, I guess. There are a couple of comments in the chat, but I think I might have answered them. So, okay. So now there is still one more issue with this idea of momentum, like which I think was explained here, right? So it is a good idea to have momentum, but it is also dangerous in the sense if you have too much momentum and suddenly you have an adversarial scenario like this, like so you are almost there to the minimum, but there is a small bump and there is a local minimum, right? Now, if you gain momentum, like it is, if you accelerate, you need time to decelerate, right? Like so you cannot like the ball cannot immediately stop here. It will definitely move a little bit further, and in this case, like it could go and get stuck here, right? So how do I avoid this? Yeah.
Use the memory of the spot with the lowest loss you were ever at.
Okay, that is a good point, but then the problem is, what if you don't touch this point at all? Like so, like for example, sorry, let me draw a better. Okay, for example, the ball was here. Okay, maybe by the next gradient step you are already here. So then you can't checkpoint the minimum, right? So how can I avoid this issue? Okay, well, maybe let's take a break. It's 1:35, so think about how to avoid this issue, and we will talk about it after the break at 1:40.